Welcome to another module in this massive open online course. Right? So far in the previous modules we have looked at estimation, channel estimation, in particular MIMO channel estimation. In this module we will start looking at another aspect of wireless communication, that is channel equalization, that is equalization of a wireless channel. So let us start looking at channel, or what we term as channel equalization, and this can be motivated as follows. Channel equalization, typically in a wireless channel, as we have already seen before, the received output symbol at time k, yk, equals h, this is the model for a typical wireless channel, h times xk plus vk, which is the noise. And what is yk? Yk is symbol received at time k. Just to refresh your memory, symbol received at time k. H is your fading channel coefficient, H is the fading channel coefficient, in fact the flat fading channel coefficient. Xk is the transmitted symbol at time instant k. What is this? This is transmitted symbol at time k, and Vk is basically the noise sample, the Gaussian noise sample at time k. So I have the system model which can be described as yk equals h times xk plus bk. Yk is the received symbol, h is the fading coefficient, xk is the transmitted symbol, vk is the noise sample. And observe that in this model the received symbol yk depends only on the current transmitted symbol xk. So this is a very subtle but an important aspect, that the received symbol depends only on the current input xk. So let us observe this, let us note this about this model. So observe that in this model observe that the current output yk, or the current symbol output or symbol yk depends only on the current input symbol xk. It depends only on the current input symbol xk, right. So the current output symbol yk depends only on the current input symbol xk. However, we might frequently have another scenario which is an undesirable scenario in which the following occurs. So frequently also it might happen that we have yk, the received symbol yk is given as h0 times xk plus h1 times xk minus 1 plus vk, which is the noise. And if you look at this model, you will observe that this is yk, this is again the current symbol at time k, xk is the current input symbol, that is transmitted symbol at time k, that aspect is fine. However, we also have something very interesting. We have also xk minus 1, that is the transmitted symbol or the input symbol at time k minus 1. We have the transmitted symbol xk minus 1, this is the transmitted symbol. To write it down, this is the transmitted symbol at time instant k minus 1. So, what we are observing is that unlike previously where the received output symbol yk depends only on the transmitted symbol xk at time instant k, what we have in this scenario is the output symbol yk depends not only on xk, but it also depends on the previous symbol, that is xk minus 1. So, let us write this down, since this is an important aspect. That is what we are observing. Basically, we observe that the output symbol, output symbol yk at time k depends not only on xk, but also on the previous symbol, that is depends but also depends not only on xk, but also the previous symbol xk minus 1, that is yk depends not only on xk, but also the previous symbol xk minus 1, basically, which means that the previous symbol xk minus 1 is interfering with the current symbol xk, that is, it is causing interference in the detection of the current symbol xk. This is known as inter-symbol interference. All right. So, essentially xk minus 1 is, to put it, this is interfering, correct? This is interfering with xk, xk minus 1 is interfering with xk. This is termed as inter-symbol interference or ISI. So, this phenomenon is termed as inter-symbol inter-symbol interference or ISI, where the previous symbol xk minus 1 is interfering with the current symbol xk, that is yk has the effect of both xk and xk minus 1. This is termed as inter-symbol interference, and naturally this ISI or inter-symbol interference leads to performance degradation, because there is interference, because xk minus 1 is interfering with xk. This leads to performance degradation, correct, at the receiver. So, this is an undesirable effect. So, this ISI leads to performance degradation naturally and is undesirable. and is basically ISI is intersymbol interference is basically undesirable. Hence, therefore, we would like to remove intersymbol interference. That is what we would like to do at the receiver for the detection of xk. That is, we want to infer what xk is. We would like to remove the interference from xk minus 1. And this process of intersymbol interference, that is, this removing this intersymbol interference, is termed as equalization or channel equalization. So, channel equalization is nothing but removing the effect of intersymbol interference to improve the performance at the receiver. So, removing this intersymbol interference, essentially removing this ISI or intersymbol interference is basically what is termed as equalization. So, let me write that down. Removing intersymbol interference. Is termed as this process of removing intersymbol interference is basically what is termed as equalization, correct. So, this process of removing the effect of xk minus 1 on xk is termed as, or basically removing this interference from xk minus 1 on xk, or the intersymbol interference is termed as equalization. And further, I would like to also point out that the intersymbol interference need not be restricted to xk minus 1, it can be on a larger number of previous symbols. So, here in this system model, if we look at your system model over here, I can in general have, that is yk, that is for a general L, for a general scenario, I can have yk equals h0 xk plus h1 xk minus 1 plus h2 xk minus 2 plus so on hl minus 1 xk minus l plus 1 plus vk, correct. Therefore, you have L channel taps. So, you have H0, H1, H2, HL minus 1. These are the coefficients, these are known as channel taps. So, H0, H1, HL minus 1, these are known as the channel taps. These are basically your L channel taps. Okay. So, we are saying for a general system with intersymbol interference, yk equals h0 xk plus h1 xk minus 1, so on and so forth until hl minus 1 times x k minus l plus 1 plus the noise sample vk, and therefore, you have L channel taps h0, h1 up to hl minus 1, and therefore, as L increases, the severity of ISI or intersymbol interference increases, which means more and more symbols, previous symbols xk minus 1, xk minus 2, so on interfere with the current symbol xk. So, as the severity as L increases, the severity of the ISI increases, all right. So, that is basically the idea, and then that what you said is basically we want to remove the effect of this intersymbol at the receiver, that is termed as equalization, and that can be done as follows. What we will do is to basically detect xk, we will also employ xk yk plus 1 and yk plus 2. So, previously for a flat fading scenario, To detect xk, we simply employ the received symbol yk. However, now because there is inter-symbol interference, we will not only employ yk, but we will also employ yk plus 1 and yk plus 2, which is what I am going to illustrate now. So, equalization, for equalization, okay. Of course, let us go back to a simple scenario with L equal to 2. Let us employ yk plus 2, yk plus 1, yk, that is we are employing 3 symbols or basically r equal to 3 symbols. So, this is known as a 3 tap equalizer. So, we are employing r equal to 3 symbols, that is yk plus 2, yk plus 1, yk. This is known as a r tap or basically 3 tap. This is known as an r tap or 3 tap equalizer. And what we are going to do is basically we are going to linearly combine these symbols, alright. So, we are going to linearly combine these symbols to eliminate the effect of inter-symbol interference. So, first let us write the system model for these 3 symbols yk plus 2, yk plus 1, yk. So, you can see that, well, yk equals, well, h0 xk plus h1 xk minus 1 plus vk. Now, yk plus 1 will be similarly h0 xk plus 1 plus h1 times the previous symbol, that is xk plus vk plus 1, and similarly yk plus 2 equals h0 times xk plus 2 plus h1 times xk plus 1 plus vk plus 2. Now, what I am going to do is I am going to stack these symbols yk plus 2, yk plus 1, yk as a vector, and you can see now I will get the system model. So, when I stack these as a vector, what I will get is yk plus 2, yk plus 1, this is the vector. Remember, we can call this the vector y bar k, which is an r cross 1 or basically a 3 cross 1. Remember, we are looking at a 3 tap equalizer. So, I have an r cross 1 vector. This is equal to the following matrix h0, h1, 0, h0, h1 0, 0, h0, h1 times now my symbols xk plus 2, xk plus 1, xk and xk minus 1. Let us call this your matrix H, let us call this your matrix, your vector x bar k plus your noise vector. The noise vector is basically vk plus 2, vk plus 1, vk. So, basically what you can observe is here we are considering an L equal to 2 tap channel, because we have h0 comma h1 as the channel taps. So, we have L equal to 2 taps, r equal to 3 tap equalizer. So, you have your r equal to 3 tap equalizer. So, this y bar k is basically a 3 cross 1. Now, this matrix H you can see is R cross R plus L minus 1, that is 3 cross 3 plus L equal to 2, 2 minus 1. So, 3 cross 4, x bar is R plus L minus 1 cross 1. So, this is 4 cross 1 and V bar k is simply R cross 1, that is 3 cross 1. So, now we have written the vector model for this input for this basically intersymbol interference channel, which is basically y bar k, which contains the symbols yk plus 2, yk plus 1, yk equals the matrix H, which is formed out of the channel coefficient, which is an R cross R plus L minus 1 matrix, where R is the number of taps in the equalizer, L is the number of taps of the channel coefficients, times x bar k, which is R plus L minus 1 cross 1, plus V bar k, which is the noise vector, which is R cross 1. And now we would like to design our equalizer. So, let me just write this down again to summarize this thing. If we consider an R tap equalizer, so I have y bar k equals h times x bar k plus v bar k, where this is R cross 1, this is R cross R plus L minus 1, this x is basically R plus L minus 1 cross 1, and this V bar k, this is simply an R cross 1 vector. And we would now like to design an equalizer. Remember, we said we would like to design the equalizer based on the 3 symbols yk plus 2, yk plus 1, yk, and we would like to linearly combine these symbols yk plus 2, yk plus 1, yk. So, let the combining weights be C0, C1, C2. So, let the equalizer weights or let the combining weights be C0, C1, C2. Therefore, now you can denote this equalizer. So, I can denote this equalizer by C bar, which is C0, C1, C2. This is, remember, observe this, this is an R cross 1 vector, this is R cross 1 or basically 3 cross 1 vector. This is the equalizer. Also, we can call this as the equalizer vector, and our equalizer therefore is now given as C0 times yk plus 2 plus C1 times yk plus 1 plus C2 times yk, which is basically, this is basically the linear combination of yk plus 2, yk plus 1 and yk. This is basically your or weighted linear combination, let me put it that way. This is your weighted linear combination of the outputs yk plus 2, yk plus 1 and yk. So, what we are saying is basically we have a 3 tap equalizer which comprises of the weights C0, C1, C2. These are the 3 taps of the equalizer vector C bar. And now what we are doing is we are taking the outputs yk plus 2, yk plus 1, yk, we are linearly combining them using these weights as C0 times yk plus 2 plus C1 times yk plus 1 plus C2 times yk. This is the operation of the equalizer. So, we would like to design the weights basically C0, C1, C2 so as to eliminate the intersymbol interference for the detection of xk, and that is the problem of equalizer design. So, what we have done in this module so far is to basically motivate this problem of intersymbol interference, where we have the current symbol yk depending not only on the current input symbol xk, but also the past symbols xk minus 1 and so on. Alright. So, this is known as intersymbol interference, and intersymbol interference leads to performance degradation, which has to be removed at the receiver. This is known as equalization, and for equalization we have to design this equalizer. The equalizer is basically nothing but these are the coefficients or the weights C0, C1, C2, which linearly combine the output symbols. That is, if we consider a 3-tap equalizer, linearly combine the output symbols yk plus 2, yk plus 1, yk to basically equalize or remove the intersymbol interference towards the detection of xk. So, how exactly do we design this weight C0, C1, C2, or how exactly we design this equalizer, that we are going to look at the next module. Alright. So, let us stop this module here.